Buenas tardes.
Felipito, ¿será que comí?
Vamos a esperar un poquito hasta que lleguen más de la mitad, por lo menos. Aló. ¿Me escuchan todos bien?
Sí, profe, ¿cómo está? Buenas tardes.
Me tuve que mudar de habitación porque había mucha música a todo volumen en la otra. Que tenemos los mismos problemas los estudiantes y los profesores.
Solo nos...
¿Solo?
No, profe, nada, perdón. Fue un ruido.
Ok. Bueno, creo que estamos la mayoría. Vamos a empezar. Entonces vamos a... Ok. Solamente quería hacerles un comentario. Recibimos toda una encuesta que hicieron los estudiantes respecto de los cursos online. Aparentemente se han detectado, digamos, distintas modalidades que están asumiendo los profesores. Algunos están tratando de mantener el mismo paso que tendrían en el semestre normal en presencial, y mientras que otros, bueno, están dando el curso al ritmo que permiten las herramientas del web, que yo creo que son necesariamente más lentas por las circunstancias de cada quien en su residencia, y además la manera de comunicarse vía estas herramientas, ¿no? Por más buenas que sean, yo creo que siempre la materia resulta un poco más lenta, ¿no? En su entrega, de manera que vamos a tener una reunión para unificar los criterios al respecto de esto, ¿no? Yo entiendo que deberíamos tener, toda la materia debería entregarse en contacto por vía de esta herramienta y no suponer que los estudiantes van a hacer más trabajo independiente, ¿no? Entonces, vamos a discutir eso con los profesores y vamos a tratar de unificar criterios alrededor de ese tema, ¿no? Entonces, por lo menos mi predicción al respecto de cómo van evolucionando las cosas es que vamos a necesitar un poco más de tiempo una vez que regresemos y entonces se prolongará el semestre para tanto contemplar todo el material que estaba planificado y digamos, salvarla un poco las lagunas que hayan quedado por las deficiencias de esta manera de entregar el curso, ¿no? Entonces, les informaré el resultado de esa reunión, tanto con la escuela como la canciller, y bueno, seguimos. Bueno, entonces, no sé si tienen algún comentario respecto de esto o respecto a alguna pregunta
Profe,
respecto a la materia. Ajá.
¿cuándo se llevará a cabo esta reunión?
Esta misma semana va a ocurrir. Lo que pasa es que la asistente tiene que buscar un horario donde nadie esté dando clase en la escuela para que puedan atender a la reunión y entonces, pero digamos, va a ser antes del jueves, presumo yo.
Profe, ¿y no hay algún protocolo si dura más de 2 meses de esto, de cómo hacer las cosas?
No hay, como entenderán, esto es totalmente inédito, ¿no? Pero sé que, por ejemplo, otras universidades en Ecuador están haciendo lo mismo, la San Francisco está haciendo lo mismo. La EPN, aunque está en periodo de intersemestral, ya está girando instrucciones para que sus profesores comiencen el semestre con esta modalidad. Y por otro lado, yo les comentaba también a los estudiantes, a los representantes estudiantiles, que yo soy profesor adjunto en Arizona y a mí me giraron instrucciones de allá haciendo la misma cosa, de manera que yo creo que es un poco, estamos explorando esta modalidad y tenemos que hacer, por supuesto, una evaluación conjunta con los estudiantes para ver si esto se prolonga mucho más, si podemos en un tiempo mayor se puede cubrir todo el material a satisfacción, tanto de los estudiantes como de los profesores, o si se toma otra decisión, ¿no? Entonces yo creo que eso está un poquito en fase exploratoria por ahora, ¿no?
Profe, y
Sí, profe.
lo que yo sí quisiera mencionar es que quizás si continuamos con las clases online, que sea un poco más tranquilo, o sea, que no nos acumulen con tantas cosas porque tenemos varios problemas también dentro de casa y sí complica mucho la situación aparte de lo del país. Entonces, sí quisiera que tomen en cuenta un poco eso.
La comunidad.
Sí, sí, por supuesto. Ese era mi punto inicial, ¿no? Esa era mi visión del problema. Yo estoy simplemente tomándolo con calma en el curso. Muchas veces doy una clase y solapo con la clase anterior para asegurarme de que se hubieran entendido los temas que tratamos. Por supuesto, yo pongo, por ejemplo, un deadline para la tarea, pero digamos, eso va a quedar flexible dependiendo de la dificultad que se presente para ustedes resolverla. Yo creo que ese va a ser la tónica, por eso decía que necesariamente esta metodología, como nos agarró un poco de sorpresa y estamos descubriéndola, va a ser necesariamente más lenta. Yo creo que va a tener sus beneficios y sus defectos, pues, ¿no? Entonces, eso estamos en proceso de descubrimiento en conjunto. Entonces, así como buena parte de las universidades en el mundo, ¿no? Entonces, vamos a ir descubriendo juntos, vamos a criticar el proceso, vamos a hacer observaciones y hagamos los arreglos que se hagan falta para que realmente se llegue al objetivo de que ustedes aprendan lo que estamos tratando de impartir, pues, ¿no? Esa es mi idea.
Ya, profe, muchísimas gracias.
Chévere. ¿Alguna otra pregunta? Bueno, entonces vamos a continuar. Entonces, las últimas dos clases habíamos estado, let me change to English. Last two classes we were discussing how to write the expansion for the, let me put here, interacting propagator. And we are recording, so don't worry. So the interacting propagator, we wrote in reciprocal space, right? In K omega space in this case. So G plus K and omega was in the first approximation was G plus K and omega plus G naught, and then I'm going to skip some of the well, let me write them here just for the first term, K and omega. Then we had the interaction. In the case we just had a single type of, you know, blob M type interaction, G plus K and omega. And then we had higher order terms. Okay, so we had G naught plus K and omega, VM, KK, G naught, K and omega, VM, K, G naught, K and omega, plus higher order terms. So the higher order terms will involve high orders of the interactions, which is this, the interaction M interaction only in this case, okay? Although we treated two types of interactions and how they were summed up in the previous class. So this series we translated into diagrams. So we make a correspondence between this the interacting greens function, which we drew as a double line with an arrow, and then we had the simple propagator, which was a simple arrow, and then we wrote the next diagrams like a simple propagator corresponding to this G naught. Then we had the M interaction and then the propagator coming out. So this corresponded to this term. And then we had two interactions. So we had one arrow, a blob, a single arrow, a blob, and a single arrow. Okay? And higher order terms here. So we just comparing the two ways to draw the expansion, we drew the Feynman rules. Okay, so the Feynman rules were to assign, for example, every time I have a simple line, we assign to this an I G naught plus K and omega. The double line corresponds to I G interacting. Now it's not this zero is corresponds to the free propagator. Okay, the solution. Okay, solution without interaction. Okay, and then we had a diagram which was a blob with two handles, which are not propagators. These are sort of short lines where to stick in the propagator lines. So, and this, we could have labels associated with the MKK. So this was minus IBM. Okay, let me put some indices here to be a little more general. So K1, K2. Okay, so in this diagram, you just you read it off by substituting. For every double line, we substitute one of these. For every simple line, we substitute one of these propagators here. And for every blob, we substitute one of those. and then we get the same expansion as above. You can see this factor of I, okay, factors of I, okay. Notice that we can just put a factor of I here, okay, to make a correspondence. So we make a factor of I, we put a factor of I here. So this term corresponds exactly to this double line. Now this term here, and now notice that if we have an I here, okay, you can put an I here, then with these two i's give me a -1, so I have to associate with a v a minus I1, okay? So you see why this rule here, okay, these three rules. So you put two i's, this gives you a -1, this with a minus, this one eliminates this minus, and then we get an I, which is a common factor to all the equation, okay? The same thing you do here, so you stick in an I, here you stick in a minus I, you put it here, minus I in here, you stick in a minus I in here, okay? And you put an I associated with each of the propagators, and you get exactly what you should by substituting these rules into the drawing here, okay? So is this clear? Any questions here?
No.
Okay.
Mm.
Okay. Okay. So we can move forward then. We also discuss how we could sum this up directly from the Green's function approach. So let me open here forgot to do this. Open new flipbook. This should be our class. Two, four. See how. Okay, how do we move this now? Sorry, I am still not very fluent in this thing here, so let me close this and open a new one. Okay, so I guess this is fine. Okay. Okay, so let's remember what we did before. If we have the diagrammatic expansion we had before, let me just change to blue again. So if we had a double propagator, and this was in terms of a simple propagator plus a simple propagator blob m plus blob. Okay, plus higher order terms. Then we could extract a simple propagator from this expansion, and we get 1 plus blob m propagator plus blob m propagator blob m propagator plus high order terms. Okay, and then we could add this this series here. So here we notice that this is all algebraic. Okay, this is an algebraic expression. Okay, so we could add this series here. So we have here the first power of this term here, then we have a second power here, okay, of this diagram here. So we could express this as the result of the power series, and that the result of the power series is 1 minus the blob m propagator, okay? And then we could just, this is just a C number, so I can put it in the denominator, so we could write this finally as the inverse of this propagator minus the blob. Okay? Translating these using the Feynman rules just gives me, including all the factors of I, okay? So let's put here I G naught G naught plus inverse, okay, minus then the minus I V M M K K. Okay, so now you can see that this is going to be the double propagator, so this should be I G plus, okay, and you can see now that by taking the inverse, we just get the I on top, we get the G naught plus inverse minus Vm K K. Okay, and then we can just translate this into the expression for the formulas, and so we get that G naught G plus is just going to be it's going to be 1 over we just write then the expression for the inverse of the free propagator, which is omega minus epsilon sub k plus I delta minus Vm k. Okay, and then remember that this is a simple pole, so this represents in principle the physics of some new particle dressed by the interaction. Okay, so we get omega, and then we join together the energy plus the correction due to the interactions, which is going to be this, okay, plus I delta, okay? So this is going to be the energy of the new quasi-particle, energy, okay? And so the energy gets modified in that way, so we just know that the new energy now reading of so K is going to be the free particle energy, which is h squared k squared over 2m plus, in this case, b k squared, okay? And from this, we can get the effective mass by writing this now in terms of a quadratic dispersion, right? Taking the k squared as a common factor, and we get h over 2m plus m, okay? And from this, we get the exact result we had obtained by directly solving, okay, for the For the free particle, let me just remember the expression was the algebra. Was a new effective mass. Okay, so this we write as h squared over 2m effective.
Teacher,
Yes.
in these cases, we're only considering the M functions, not L, right?
Yes. So if we do the L as we showed in the last class, we can do exactly the same thing, and we'll end up with an additional term here. So we can put.
Yes, Amairita.
Okay.
Okay. And we will, and it's also diagonal in K, so we just would add, if we had an additional L term, we would have another correction here. Okay. So by mapping these two, we get that the effective mass is 1 over 1 plus 2m times m. Okay. So this would be the effective mass of of quasi-particle. Okay. So any questions with respect to this? Okay, if we add the L term, we get another correction, which was the relativistic correction to the quadratic dispersion, and that would be it. Another comment we should make is that recall that this term. Let me put those comments here.
Professor?
Yes.
I have a question. I remember that you say that when delta is 0, is because the lifetime of the particle will be infinite, right?
Right. So I was about to make that comment now. Okay.
My question is explain in a better way what is the difference between the particle which has a lifetime infinite lifetime and finite lifetime.
Okay. So recall that here VMKK is a real number. Okay, real. It's a potential. It's a matrix element of a potential, so it gives a real. It's only a real correction to E, and epsilon sub k is real. Okay, so this means that there is no change, okay, to delta, okay, which in principle is could occur in general. We could have a change in delta due to the fact that, as you mentioned, the particle acquires a finite lifetime. If there is no contributions, okay, let's put here could be complex in general, okay? So if it's complex, then the real part changes the energy and the imaginary part changes the lifetime, okay? Here we can still, okay, so if there's no change to delta, delta can be taken to 0, okay? And as delta has dimensions of 1 over time, okay? If delta goes to 0, okay, this goes to 0, and tau goes to infinity. This means that this particle, okay, this solution is an exact solution. So the particle is an eigenstate, the quasi-particle, it's also an eigenstate of the original Hamiltonian, including the interaction. So the particle has infinite lifetime. Okay, so remember that we start with a series of levels, right? So this is the original Hamiltonian. This is the Hamiltonian H0. Okay, so here we introduce an interaction. Okay, this is the blob interaction or the L interaction. Okay, and what happens in general to these levels? Let's take, for example, this level, a particular level here. this level will get shifted, okay, in energy, and will get widened also. But what it means, remember that if we have through the uncertain relation, we have that the uncertainty in energy and uncertainty in time has to be greater than h bar, okay? So this means that the uncertainty in energy is greater than the h over delta, or so the uncertainty of time. So if this line in here, these lines are precise lines, these are delta-like functions, okay? So they occur at a precise energy. So there is no uncertainty in the energy. So this is 0. So this has to be infinity. There's no uncertainty. The lifetime associated with that label is infinite. Okay, so that means, okay, so if tau goes to infinity, it is an exact eigenstate. Okay, so that is what we found here. We made a rather simple problem so that we could find the solution exactly, and we found the solution exactly in 2 different ways. We diagonalized the Hamiltonian first, and then we did it through this diagrammatic technique, and we found an exact eigenstate. So in this problem, we did exactly this. We went from a very precise level to another very precise level here. So we have now a shifted set of levels due to the interaction, okay? But they are all, okay, so this got shifted here, and the other one got shifted here, okay, and so on. But they are very precise levels, so they have an infinite lifetime, so they have no uncertainty in the energy, okay? In general, what's going to happen is that we will start with a precise set of levels in general, okay? We'll start with a precise set of levels, okay? So let's focus on this one. So we introduce the interaction again, okay? And for example, if we follow up this one, this will move up or down, okay? And then it will also acquire a certain width, okay? So it will have, if it acquires a certain width, there's a delta E, and then this implies a finite tau, finite, okay? So it's not infinity. So this means that tau is finite, and this means that also we have a certain width. That means if I put a particle in this level, it will live there a typical time and then decay to some other state. Okay, this does not happen in this for the Hamiltonian 0, because if I put a particle here, it will be exactly in that state, okay, with a precise energy, and so its lifetime will be infinite. If I have something that has a certain width, okay, then this means that it has a finite lifetime. It decays eventually, okay? This is like also, this is well known in particle physics as what they call the resonance. A resonance is something that has a finite lifetime and then decays to some other state. This also happens here in the concept of quasi-particle, okay? So this would be a quasi-particle with finite lifetime, okay, and decays, okay? Okay, so does that clarify your question?
Yes, thank you.
Okay.
The last question is, this is for electrons, really?
Sorry?
This is for electrons, really? Sorry.
I mean, we're talking about electrons here, right? So an electron went into the pond, okay, of interactions. It interacted with an M-type interaction and an L-type interaction, okay? And then the electron gets dressed by this interaction, modifies his energy due to this interaction, and acquires then an effective mass and a lifetime, okay? This could be now the story also for a hole, or we could also dress the electron. So we can dress the electron by electron-electron interactions, or we could dress them by electron-proton interactions, and so on. But all those interactions will yield the same picture. Okay, if we put the electron-phonon interaction, then the electron gets dressed by the phonons in the system, and it modifies its energy, and it can acquire also a finite lifetime because of this dressing, okay, or these interactions. Okay, is it clear?
Yes, thank you.
Okay, so one thing that we had invoked in this particular expansion was the fact that in order to make this correspondence here, remember, we were thinking about making the combination blob propagator smaller than 1, so in principle these two, this series converged. But then, you know, came Dyson with the idea of expressing this in a slightly different way, which was to express the infinite expansion in the following way. So we see that this answer is a little even more general than we thought before. Okay, so we have the double propagator is a simple propagator, and then we could express it like this. Double propagator. Okay, so this is and this is all there is, right? So the idea is to we can iterate this expression. Okay, so we can iterate. So we have here the full propagator the same as this one we have here. Okay, so we can substitute in principle this one by the propagator plus this diagram. So we let me just do one step because we did it last time. You can make specific questions now. So we have the blob, and then we can, I'm putting here a parenthesis where I put the simple propagator plus the diagram here, blob again. Okay, double. Okay, and that's it. Okay, so now you multiply this and you get the first terms in the previous expansion we had. So we have a simple propagator M, another propagator, and then we have the propagator M, propagator M, double propagator, and then we do it again, right? And doing once repeating this process, we get and again we generate the full series we had before, which was this one here. Okay. Okay, so this is actually another way to express the whole series expansion. But again, remember that we can do algebra here, and that was the whole point of going to Fourier space. So if we do algebra, then we can just solve for the full propagator. So 1 minus the propagator blob, okay, times the full propagator. This is not correct. So if we have common factor, so we get 1, and then no, let me see. Right, so yeah, I was writing incorrectly. So we have 1 minus propagator blob times double propagator. So you see that this is 1 times the propagator is this term, and then a propagator blob double propagator is this term here. So I just move this whole term on onto the other side, and we're left on this side with a simple propagator. And then the double propagator, we just divide both sides by this expression here, which is an algebraic expression, and have this 1 minus, okay? And this we can simplify to this, which is the expression we had before, simple propagator inverse minus n. Okay, so you see here that really this expression, this infinite expression, is not limited to the fact that this modulus, okay, the modulus of v m k is smaller than 1, okay, okay, this is not a limitation, okay, so this being smaller than 1, so that these series we can sum up, okay, sum up to infinite order. Okay. One comment that we should make is that if we do not sum this to infinite order, we do not get out again a simple pole. Okay. So the quasi-particle picture arises only if we do either a complete infinite sums or partial infinite sums. And I will tell you what a partial infinite sum means, but we have to always sum to infinity in order to obtain a simple pole for the interacting Green's function, okay? If you try to truncate this series at any point, it doesn't make any sense, okay? You do not obtain the the quasi-particle picture if you truncate this series in any way. So the only way is to sum up the full series, and this, of course, is a matter for mathematicians to show for which interactions you get a convergence of the series, okay? But the experience in physics is that if you consider the correct physical conditions, you should get a convergence because it's a physically meaningful answer that you should obtain from the perturbation theory. Okay, so any questions about this? So this is something we're going to put in practice immediately. Okay.
Teacher,
yes.
I don't know one part in the first diagrams. We have in the first, yes, yes. I don't understand why the first line is equal to the third line. I mean, we have like 2 graphics in the...
Two people are talking at the same time? Or what?
3.
Sorry? 2 people were talking at the same time?
Es mi hija que está...
I'm sorry.
Okay, okay. Okay, so continue your question, please.
Yes. I'm sorry. In the first line, we have like 2 diagrams, and in the third line, we have 3 diagrams. So, right. Understand.
Okay. Okay. So what I did is this is what I mean by iterating. Okay. This is something. Physicists should learn from from kindergarten to iterate an equation. So let's see how we do it. So this diagram here is exactly the same as this one, right? Okay, so what I do is iterate. So this diagram is equal to this equation again. So we have the simple propagator plus this same propagator. Okay, so this is what I did here. I put this diagram here is equal to this same equation. Okay, so here we have the simple propagator here, okay, because this double line is equal to this plus this diagram, and this is what I put here, okay? So I iterated, okay? Now I multiply because this is algebra, so we have the distributive law, so we can now multiply this diagram by this propagator and we get this, okay? And then we multiply this diagram by this diagram here, and we get Okay, propagator, blob, double propagator. Okay, is it clear?
Yes, teacher, thank you.
So you just repeat this again. So now, okay, this double line. So I put a parenthesis here and do the same again. We add the simple propagator plus the simple propagator blob. Okay. See if I can. Okay. And we put the double here and we iterate once more. Okay. And we generate the next term. Okay. We could put this in here and we generate the 3 blob term plus the 4 blob term with a double propagator, and we do it again and we do it again, and we obtain this expansion here. Okay, the full expansion here. Is it clear?
Yes, yes. Okay.
Okay, so this is what we do. And then we do algebra with this expression. So we just, from this initial expression here, we obtain this, okay? So we just put together all the terms that have double propagators together. So you see that this is just 1 times the double propagator is this term, and then minus a simple propagator blob double propagator is this one here. So here we have this other term, and then we have on this other side, we were left with a simple propagator. And then we do algebra as we would with C numbers, okay? We do algebra in the same way because everything is in K omega space. Remember, we can only do this in K omega space where we have algebra and not an integral equation, okay? So we obtain this result here, okay? So here you apply the Feynman rules and you obtain the final result, and you obtain your effective energy and your effective lifetime. Okay, now let's do now a more interesting problem so that, you know, Ariel gets his share of electrons and holes directly, okay? So let's now introduce here the holes, okay? Hole propagator. Okay? Hole propagator.
Teacher, in these cases, we are only considering one particle, right?
Yes, it's a, yes, we're doing, this is the single particle Green's function, okay? Generally, we will stay with the single particle Green's function, although 2 particle Green's functions are also defined, okay? But this is a much more cumbersome perturbation expansion, but there are expansions for 2 particle Green's functions, okay? But generally, you know, our brains are very limited, so we stay with single particle distribution functions and single particle propagators, okay, generally, and this will be enough to do many things, okay? So, and also remember that we go from the single particle, single free particle approach limit to the dressed particle limit. So in essence, we go from non-interacting particles to non-interacting quasi-particles. So this is, you know, sort of a very nice feature of nature that nature gave us with this formalism, that we need not go beyond the 1 particle picture if we can map a simple pole to another simple pole, okay? And this is generally what is, I mean, these sophisticated techniques that we use in these quantum mechanical packages. Essentially, this is all that's behind those single particle propagators. It's all that's behind it. Of course, you can do some more sophisticated calculations, but with 2 particle propagators, but you can bypass them by using other concepts like linear response theory and these kind of things. Okay, so you'll see this in graduate school if you're interested in this topic. Okay, so until now we had only defined. Let me put the blue back in. We had only defined the G plus. Okay, so this describes electrons. And let me put G naught. Okay, electrons above the Fermi sea. Okay, and propagating forward in time. See if I can, after this class, I'm going to learn how to have this pen a little thinner in time. I may spend half an hour if I do it now. Okay, so what if we have holes? So holes are now described by a free propagator with a minus, okay? So what's the difference between the two? So let me define as I did for the retarded propagator. Now we're going to have the advanced propagator minus, and we're going to have K2, K1, T2 minus T1. So the ordering of the times is going to be the same, okay? This is going to be, and this is only defined for now T2 less or equal to T1. Remember that this was the other way around for the retarded propagator. And this is going to be the probability amplitude, okay? Probability amplitude, okay? That if at T2, we add a hole okay, in phi K2, which is a state of a missing electron, to the interacting system, in the ground state. Okay, then at T1 will be in the ground state. One second, let me finish the definition. With a hole in phi K1. Okay? Yes?
It says we add a hole in phi K2 to the interacting system, right?
Let me in the interacting system, I mean.
I need to know what is interacting, the INT? Or...
In phi K2, in the interacting system. Okay, in the interacting system, it is sort of badly worded. Let me see, probability amplitude that if at T2 we add a hole in phi K2 in the interacting system, in the ground state of the interacting system. Let me, okay. Okay, then at T1, we will be in the ground state with a hole in phi K1. Okay, this is the probability amplitude that this transition is made. We introduce a particle, a hole in phi K2 at T2, and then the probability amplitude that we will have then a hole in phi K1 in the ground state of the interacting system. Okay, so this is completely analogous to the previous definition, except that we are going back in time. Remember that T2 in the previous definition was greater than T1, so here we go back in time. And so we will see how this happened in terms of the propagator. So put an additional here. So we have analogous definitions that for this one. So we have, let me change to here. So here, so for T2 greater than T1, G minus Ig minus is equal to 0, okay? And I forgot something here. This has a minus sign here. Okay? And this is a factor like with the I, we have to put a minus sign here because of the backward propagation of the particle. Okay, so for T2 greater than T1, we have minus Ig minus is equal to 0, the same way that the other one was for this one, it was, for this situation, it was different from 0, and from the other situation, T1 greater than T2, it was 0. So this is the other situation. Okay, and we have now an expression also for the free particle propagator here, as we had before. So this will be in KT space. It will be I theta T1 minus T2. So this changes from the previous propagator. Then we have the exponential minus I epsilon T2 minus T1. Okay? And this is for T2 different T1. Okay? And the other thing that we're going to now emphasize is that this means that the energy is below the Fermi energy. So you can only make holes below the Fermi energy. Okay? And this will be I for T2 equals to T1. Okay? So this is just, I put this second condition just because we don't know what this theta is at T equals to T1 equals to T2, because it's jumping at that point. So we just make this ambiguity here, we make it definite by defining this other condition here. Okay? And in K omega space, we have that this propagator minus in K omega space is going to be 1 over omega minus E sub K. And now here also changes, the convergence factor has now a minus sign. Okay, so this corresponds to this sign here. Okay, remember that for the other one we had in K omega, we had this was omega minus EK plus I delta, and this corresponded to this plus here. Okay, any questions? And in this case, we had EK greater than KF. And in this case, we have EK smaller than KF. Okay, these are holes, these are electrons. Okay? Okay, so these are all the rules now for the propagators that contemplate holes. Okay, so let's now give you the Feynman rules. Okay, and we're going to write our expansion now for now a more interesting process in terms of the following Feynman rules. Okay, so K omega space, and we're going to work in K omega space directly. So we have I G plus K2, K1, and omega is going to be going to correspond you get it confused with the propagator, so this is going to correspond to the double line. Okay, this double line will have the two labels here and the single label here, and then we have the full propagator for the minus, okay, for the holes K2, K1, and omega will be corresponding to the propagator now in the other direction, okay, K2, K1, and omega, okay, and then we have the free propagators, which are going to be I, G naught plus, okay, they have a single wave number and a single frequency, and now we're going to write them like this, much more explicitly than we did before. So we're going to put explicitly the condition that epsilon sub k has to be larger than Fermi energy, okay? And this is written like a simple line going to the right, and omega minus ek plus I delta, okay? And then we have the whole propagator, okay? And then we have I theta, and we switch around Pf minus E sub k. So this tells me that I can only have these propagators below the Fermi energy, okay? Omega minus Ek minus I delta. And this obviously is an arrow in the other direction. Okay? So now we have the full expressions, and we're missing something here. And so now we have I, B, K. Okay, let me put it like this. So we have a single type of interaction, so I don't need to put an M or an L. Okay, so this is the potential. This is the matrix element between K and L. Okay, but now this corresponds to a more rich types of interaction. So you can have something like this. The interaction can couple two free propagators to the right, okay? Or the interaction can couple to free propagators to the left, okay? Or you can have something even more interesting, which is a propagator going to the right and one going to the left, or the other way around. One propagator going to the left and one going to the right. Okay, all these possibilities now arise in this when we have holes and electrons simultaneous. Okay, so these are the Feynman rules. Feynman rules. Okay, and we must we know once we write the expansion in terms of the diagrams here, we know how to translate back into the Green's functions, which we know their functional dependence exactly in K omega space. Remember, okay? This is K omega space. Okay, so let's see what we can do with this. We'll see how interesting this gets. Okay, so now we have the interacting propagator to, okay, for electrons, okay? let's do this in the time domain first, okay? So that we can understand physically what's going on. So T1, T2, okay? So, and we have T1 at K1, or K1 at T1, and K2 at T2. Okay, again, this is going to be the simple propagator. Okay, again, K1, K2, K1. Okay, this is let me put this, and you know there's a delta function there, and this will be a T1, T2. Plus, then, as we had before, we have K1 propagator forward. Okay, propagator forward like this. So we have T1 at intermediate time T, then final time T2, and we have we know that the free propagators just have one K1, and then the other one will be K2. Okay, and then we can do this again with the three blobs. So we have so we would have two intermediate times. Okay, three propagators like this. So you know this starts in T1 and ends in T2. And now we have two intermediate times here, T and T prime, okay? And we have one intermediate. So we start with K1. We have an intermediate Q propagator here. And then we have a K2. Okay? And then we can continue with this series like this. But then we get terms like, we can also get terms like this. Okay, and this is going to be the interesting one. So we go now forward. Let me draw it a little larger. Okay, we get something like this. Then we can get a backward propagator. Okay, and what matters, remember the timeline. Okay, so we only have, the timeline goes like this, right? So this is T. The fact that it's going down doesn't mean anything. The thing is that it has a projection going back in time. So this is a whole propagator here. It's just because of the limitations of the drawing that I'm not going to overlap it with the previous one, okay, for the effects of the drawing, and then we go something like this. Okay, so this is an extension of this second order in the interaction diagram here. Let me draw again the time. So we have time T1 here, then we put time T here, then we can put T time T prime here, and K2, K2, this is K1, and then we have some intermediate, and let me put the intermediate as an L here. Okay. So let's see what this diagram. Then you can have some more the higher order terms here. Okay. So I'm going to tell you about this expansion here because this comes to the concept of precisely summing an infinite set of diagrams, but choosing the appropriate infinite subset of diagrams. Okay. So let's see what this means. So let's walk this diagram again. Let's make the lines first. Okay, so this is T2, T1, okay, K1, L, and K2. This L corresponds to this line here. Okay, so what does this mean? So again, we just follow our noses here. Okay, at T1, we introduce a particle in the state K1. Okay. Then you see that I forgot to put the intermediate time, so I'm putting here T prime and T. Okay. So then at time T prime, which is before T, okay, because the time is going in this direction, okay, time is going here, okay. So at time t1 we introduce a particle in k1, but the interaction at t prime knocks out a hole in the state L into state k2, okay, so this happens at time t prime, okay, and then at time t, the interaction knocks the electron in the state K1 into the hole left by the previous interaction. Okay? So this is clear. So you introduce a particle here. Okay? Maybe we can draw sort of let's try to draw it here. So I introduce a particle here, K1, okay? Okay, let's suppose it's propagating in this direction, okay? And this is the Fermi energy, okay? But suddenly the particle, the interaction, sorry, at time t prime, knocks out an electron from below the Fermi sea into state K2. That happens at t prime. Okay, so this happens at T1. Okay, at time T prime, then at the interaction knocks out an electron from below the Fermi energy. This is state L, okay, and knocks it into the state K2. This is what happens here. It knocks out this electron that is below the Fermi energy. It knocks it out into state K2, which is above the Fermi energy, okay? And then at a later time, t, okay, let's suppose this hole is now propagating here. The K1 state is knocked into the hole, okay? And this particle ends up in the final state, okay? We will do this in second quantization now, but do you understand what's going on? Any questions about this?
Could you repeat the process one time, please?
Okay, so again, drawing this is not so easy. So we introduce a particle in state K1 at time T1, okay? And we follow the timeline. So this is the timeline. So what happens first? What happens first is this time prime here. So we have this blob is the interaction, right? Interaction. So the interaction acts and knocks an electron, which is below the Fermi energy, from state L, okay, into state K2, which is above the Fermi energy. This is why I drew this. So the interaction, so let's suppose we have the interaction here, V, and this knocks out the electron. Remember that until now we have just single particle interaction. So this is the action of an external electric field, okay? You may think that, you know, this external electric field is quantized and it has some quanta that hit the electrons, okay? So this quanta hits the electron out from below the Fermi sea into state K2. So this is what happens here. I knock out the electron that is in state L below the Fermi energy, because this back propagator corresponds to electrons below the Fermi energy, okay? Knocks it out into the state K2. So this is what happens here. I knock it out, the interaction, okay? So knock it out here, okay? And it starts propagating in this piece, which is the timeline. So here we have simultaneously a particle above the Fermi energy in K1 and a particle above the Fermi energy in K2. These are these two particles here, K2 and this one K1, that nothing has touched it yet, okay? So when we proceed, the next time step is T. So at this time step, what happens? The interaction knocks this electron into the state L, which is unoccupied because there's a hole that was created previously, okay? So this one gets knocked into the hole, okay? So this is what I mean by this thing here, K1, which has been propagating forward, it gets knocked into the hole and it disappears, okay? And at the end of the diagram, we end up with a single particle at in state K2 at time T2. Is it clear now? Is it clear?
Yes, Professor. Sorry, I cannot turn on my microphone. Yes, thank you.
Okay. Any other questions? Let's do this with the second quantized form, which we are now experts in. Okay. So let's draw this. What's going on? So the first step. Let me draw the diagram so that hopefully you will agree that the second quantized form I draw corresponds exactly to what the diagram does. Okay, we have this state L, state K1, and then we go this direction K2. Okay, and these are the interactions V. Okay, second quantized language. Okay, so how do we represent this? So at time T1, what do? We apply, we introduce a particle, so we create a particle in the Fermi vacuum. Okay, this is the Fermi vacuum. Okay, vacuum. I hope that that's not somebody's stomach. Okay, so we create a particle. Okay, we create a particle in state K1 in the Fermi vacuum, which is an interacting. Okay, this is the interacting ground state. So this is trying to making contact with the definition of the propagator. So what happens now at T prime? Okay, so this creates then one particle, okay, in state K1, and let's emphasize this is a particle with a P at the top, okay? So now we have this state having introduced, okay? Before time T1, the T prime, we have just this state here. So now the interaction, and we put this like this, so the interaction connects state K2 to state L, okay? And we create a particle in K2, and we create a hole in state L, you see? And this we apply to the previous state. So the previous state was this one, okay? So you see the interaction is the one that's coupling the state L to the state K2, okay? And this is applied to the situation where we have already a particle in state K1, okay? So this is equal to what? This will be equal to K to L, okay? And now we will have a particle in K1, okay? Which hasn't disappeared. We will have a hole in state L, and we will have another particle in state K2. Okay? So that's what happens at time T prime. Okay? Now we're in this state. Okay? So we have these three particles simultaneously, 2 electrons and 1 hole. this is an intermediate state, okay? So at time t, okay, at time t, now with the interaction again operates, it's connecting now the whole left of the state L with the state K1. The state L just says that it's a state below the Fermi energy. We're going to destroy a hole that gets filled by the electron in K1 and destroy an electron that was in K1. Okay? So this we apply to the previous propagator. Let me put it like this. So we have K2L, okay? And then we have the state, we do before, K1 particle, 1LH, K2P. Okay? What do we end up with? So we just end up with the product of the two interactions, K1, K2L, okay? And here, this destroys a particle here, so we make a hole here, okay? No, we don't make a hole. This is a particle, so this is above the Fermi energy, so we just make this one disappear, okay? We also destroy this hole, which is below the Fermi energy, and we end up with one particle in K2. This is it. Okay? And what do we do at the end? At T2, we can think of, okay, this process as we extract a particle from the state K2. So this is the K2L, VLK1. And we're left with just the action of the two interactions that we had in the Fermi ground state. Okay? So this just annihilates this particle here, and we're left with the Fermi vacuum. This is clear? Okay, because in the homework, I'm going to put you a few of these interpretations that we do of the diagrams in terms of second quantization. Any questions? So this is something you have to digest. You see that the whole process I have put in second quantization, and at the end of this section, I'm going to tell you about how we can use second quantization to express the free particle, the interacting Green's function in terms of second quantized, but with a time ordering included. Okay, so this is going to be sort of the end of this section on diagrammatics. We're going to see the most formal way, compact way in order to describe these propagator using precisely this type of description. Okay. Any questions? Okay. So,
sorry, Ernesto.
Yes.
Could you repeat the last part at T2? What happened?
At T2, okay, so at T2, I introduce a final. So this is an extract a particle at K2. Okay, so this is what I did here. Okay, so in principle, this will be the end of the story, right? So this is still at time t, but then we're calculating the amplitude of finding a particle, okay, at K2. So we sort of extract. This is calculated by extracting the particle from the ground state, from the interacting ground state, and we get this amplitude. This will be the amplitude here. Okay, so that's it. So we extract the particle at K2 at the end. So we put it in at the beginning and we extract it at the end, and we're left with the untouched Fermi vacuum. Okay, and the amplitude for having a particle in that state, and that depends on these interactions. Okay, so this is going to be a contribution for the amplitude of having introduced a particle at T1 and then extract it at T2. Okay.
Okay, thank you.
Okay. So this is, you see, this is a very physical way to understand the interacting problem. So you can basically use your imagination with some rules. Okay, you have to educate your imagination, as you will see when we develop this with more realistic interactions. Okay, and so you just imagine all the possible ways, all the Feynman paths that can occur in the system. Okay, and then you calculate and you choose a subseries, or if you can, you sum over the infinite series of these interactions, and you extract from this a simple pole structure which you identify as the propagator for the quasi-particle. Okay, so this is the idea. Okay, so basically what we will do when we get series about, for example, including now the Coulomb interaction, is that we're going to find subsets of diagrams which are more important than others. Okay, so this has been sort of the story with this. This is the story also with quantum electrodynamics and with quantum chromodynamics and with other areas where these the diagrammatic expansions are used. To identify which subset of diagrams are actually the most important ones. Okay, so for illustrative purposes, let's assume that we select important diagrams. And this is how the RPA approximation was also discovered. Okay. So this is actually research work. When you find out which diagram really, or which series of diagrams are the important ones, then you're doing research. You're breaking the edges of science. Okay, so let's suppose that only VMK, okay, with a specific, and this is just for illustrative purposes. I'm not, we don't have any specific form of V in this example, so I don't care what the form of V. I'm just stating that VMK with a specific M and K is important. Okay, all the others are very small or zero. Okay, all others being small in relation to VMK. Okay, all other matrix elements I can take to be zero or not important. So what does this mean for the expansion? This means for the expansion, now that I have a double propagator, okay, so this will be now K, and I'm going to choose K, which is this K here, okay, so this is also K omega. This is going to be one of the important Ks, one of the important momenta, okay, and then we're going to have this guy, okay. And the important thing is that everything is going to be labeled by omega, but this is going to connect K and M, and this is going to connect back M to K, because these are the only important matrix elements that there are, okay? And then we can have a double process like this. We can have a K going in, like all the Ks that are going in, this goes with K, goes in with K, goes in with K, and then it can go to M, and then it can go to K again, and then to M again, and then to K, okay? And then, okay, and you continue this trivially, okay? Notice that I'm sort of slanting this so we can have this dot is before this one, and this one is before this one, and this one, okay? And this one is after this one, and so on, okay? And this would be now my expansion here. Notice then that we can do exactly the same trick, and this is always the same trick, okay? We can extract, okay, omega omega as a common factor, and we have now 1 plus, and we have a blob, okay? We extract the 1, so we only left with this one here, and then we're going to have the same. This is with the intermediate, so let me just label this will be M and K, and this will now be log K M squared, okay, and so on, okay? So we repeat here we extract this guy, and we're left with this guy and this guy, so that's the square, okay? Here we extract this K propagator, and we're only left with this one, so we have this one, and you see now we have again the same power series we had before. So this is very nice. Again, we can apply either of the two arguments we did before, and this will be equal to a propagator times 1 over 1 minus log M log K and M. Okay? And this will be the double product. And this again, exact sum. Okay? So okay, so you see that now I can sum exactly that subseries. That this was an infinite, because this doesn't include all the diagrams, it includes an infinite sub-series of diagrams. Okay? But we sum it to infinity. We choose the ones that are most important, and we sum that to infinity, and we use that as an approximation to the actual results. So this is okay. Okay, so we can simplify this as we did before. We passed the diagram. You remember that this propagator has the same momentum as this one. So this we can simplify simply this. This will be K inverse and D. Now we have minus, and we have D G minus naught here, okay, with momentum M. Okay? Notice that there are two interactions here. So there's a V here and there's a V here, okay? So, so let's translate this now. Feynman rules. Feynman rules. Okay, and this, okay, we know how to translate. This is the forward propagator, so this is G naught. Okay, this will be 1 over the long line here, so omega minus E sub k plus I delta. Please at home translate this using exactly the Feynman rule, so you get the factors of I, and you satisfy yourself that the I's are not getting the wrong answer, and then we get minus. Okay, this will be K M and M K. Notice that they're switched, right? Because one converted K to M and the other one converted M to K. So we have the the two combinations, and then we have the G minus, and the G minus is going to be 1 over, okay, omega m minus I delta. Okay, so you see we have two energies here. We have one m energy and one k energy. Okay, and this here is G naught minus at wave vector m and frequency omega. Okay, and this here will be the modulus of k. Okay, any questions up to this point? Let me get my charger because my computer is running out of energy. Hello, I'm back. So any questions about this?
No, teacher.
No.
Everything is clear? Okay, so let's finish this. So again, this is the full propagator, remember? And again, we obtain through this procedure, we obtain a simple pole. But where is the pole? Okay, so we have to solve for the bottom equation here. So what's the bottom equation? So let's make a new, okay? So this will be the equation. So that's the position of the pole is going to be here. Okay, and we can take delta to 0 because again, we don't have any corrections that have an imaginary part. So we have just this, okay, taken delta to 0. Okay, so we have to solve this equation, but this is a very simple equation. This is will be a quadratic equation in omega, and we will get now that the E k prime is going to be the solution of this omega, the second order equation, and this is going to be ek plus em, okay, plus 1/2 square root. This is just solving the quadratic equation. This will be ek minus em squared plus 4k km squared. Okay, so actually my pole now signals not just one but two solutions. Okay, two solutions. Okay, this is just because this is a quadratic equation, then we get two solutions, so we have two quasi-particles. Okay, again they're with infinite lifetime. Okay, notice that this is just a solution, and we could stop here and discuss a little bit more next class. This is just the same solution as a two-level system. Okay, where we have a particle above the Fermi energy, okay, and a particle below the Fermi energy. Okay, K and M, and this is exactly the same solution that would come from having these two levels and coupling them with, if you solve for the eigenvalues of this Hamiltonian, you will get exactly the same solution as we got before. So we actually solved another trivial problem. Okay, this is trivial to calculate, okay, by diagonalization, okay, and we obtained the same solution through this diagrammatic approach, where we just couple these two levels, okay, through the electron-hole interaction, p-hole interaction. Okay? So any questions here? I think this is quite an extensive example, so you should digest it tonight. Because the next step is to go seriously with now the Coulomb interaction and you know, see all the problems that arise with the Coulomb interaction, but actually obtaining something that you see in a real Fermi gas. Okay. So next class we're going to see make contact between what you used to know as a Green's function approach and this approach, to see that they're one and the same, okay? We'll make a connection between the two, and we'll show that the solutions that we mentioned before for the single particle propagator can be obtained using the regular, or the most familiar, Green's function approach, which is this solution here. We're going to prove that the regular Green's function approach produces these results correctly. Okay? Okay, so if you have any questions, now's the time. If not, we meet again tomorrow. If you have questions about the homework also, please bring the questions about the homework tomorrow, so we can sort of do a recitation and class combined, so that you clarify questions from the homework. Okay?
For me, no questions, teacher. Thank you.
Okay. Okay, so good. So let's stop here and we meet again tomorrow. Let me stop here the stop recording.